There we go. All right, so today we're gonna discuss Radix Sort. We have actually, like, there's one thing before I just carry on with this. We have discussed heap sort before, if you haven't forgotten yet. So we discussed when we discussed the heap, we also discussed the heap sorts, right? So in the heap, you are like you do the heaping, or sorry, heapify. So you satisfy the condition of how heap is being constructed, and you just simply keep returning an element from the heap, and then just simply push it back into the array where it comes from. And the moment you fill up the array every time, until the end, you actually end up with a sorted array. So this is what heap sort was about, if you remember. So Adil will cover with you the implementation detail this week, hopefully. And so far what we have covered was bubble sort, selection sort, insertion sort. What else was it? The heap sort, we have actually like touched upon it when we were discussing the heap. Merge sort, quick sort, right? Merge sort and quick sort being under the category of divide and conquer algorithms, right? So we have discussed like a variety of algorithms so far. However, Radix sort is actually kind of important. Not kind of, it's actually super important, I think, to learn about, because it actually discusses a different way of sorting a list of elements, or a collection of elements, rather. And the idea here is, if you have noticed, most of the sorting algorithms which we have covered are actually comparison-based algorithms, or comparison algorithms. So basically, what a comparison algorithm is like you, in fact, grab, for example, an item, item 1, and you are asking whether it is larger than or less than item 2, for example, right? And this is what essentially we were doing during working with a comparison sorts, right? So whether you are doing a selection or quick sort or whatever, you are all the time comparing, hey, are you larger than or less than, and all of that stuff, right? Now the problem is this stuff is very slow. It's very slow when it comes to a number of elements that are actually quite big. Okay. So if you are, for example, sorting like let's say 1,000 elements or something like that, or 2,000, 5,000 elements, it's actually quite fine to use comparison sorts. But when things start to grow really big, like we're talking about like 1,000,000 elements, 2,000,000 elements, right now things are going to get a little bit slower, even though I'm talking about a little bit slower in the grand scheme of things. But for example, a sort can take you, let's say, like 2 seconds or 3 seconds, depending on your machine which you're running on, maybe 14, 15 seconds, right, to sort 1,000,000 elements. But for example, using some sorting algorithms which do not rely on comparisons, it might actually boost the speed up quite a bunch, actually. And Radix Sort is one of those genius algorithms that they actually do not rely on comparisons when they are sorting. So you never ask the question, hey, are you larger than or less than? You just simply like it just the list gets sorted nicely. However, we use a little bit of RAM, unfortunately, as a result. So let's first discuss the differences, what's happening with why we are saying comparison sorts, why we are all Audio. Can you hear me now?
Yes, we can.
Okay, perfect. I see the fun gifts. So I don't know what was the last thing I said for you guys. I wanted to say that you cannot still see my screen apparently. So let me just share my screen. So let's discuss the reasons why a comparison sort is actually slow, and you might be able or you might not be able to beat the average of n log n with a comparison sort. Maybe you can get with the best case like log of n, but on average you might not beat even the n log n complexity. So so let's discuss this. So for example, one of the reasons, like the main reason actually behind why comparison sort is slow is because you are actually searching through permutations of elements. In fact, like if I give you, for example, a number, let's say like four, a bunch of numbers like 4, 3, and let's be like mm, let's be like 4, 2, and 3. Okay, so if you have like a number, a list of numbers that you just something like 3 elements here, and you would like actually to find the permutations, number of permutations of that list. Okay, so if you have an array which has this number of elements, so number of permutations is usually like the number of elements, so n factorial. This is like the number of permutations. And wow, actually, like my pen is offset right now. Okay, um, so n factorial, so 3 factorial is actually equals to 6. So I have like 6 permutations um, that actually allows me to like reorder, to actually like organize that list. 2 of these permutations are actually sorted. One of them ascending, one of them is descending, obviously. So for example, this is one permutation, right? Another permutation would be, let's say, 2, 4, and 3. Another one would be 2, 3, and 4, which is sorted. Okay, and then you're going to have another one, which is going to be 4, 3, and 2, which is also sorted, right? But this one is descending. Um, so we could have like 3, 4, and 2, and then we have one more, I think. So 1, 2, 3, 4, 5. We have one more 4. So 2, 3 is actually 3, 2, 4 probably. So 3, 2, and 4. Hopefully this didn't repeat anywhere. 2, 3, 4, 2, 4, followed by 3, and okay, I guess this is pretty much it. So 1, 2, 3, 4, 5, 6 actually. So we have like 6 permutations, right? 2 of them are actually sorted. Let's say that you are actually trying to sort, but you are actually trying to sort, let's say, ascending. So you're trying to sort from the smallest to the biggest. So I'm actually gonna like erase this right now. So for the time being, when you are trying to sort a list, you are actually like sorting the list in a certain way, only one possible way, right? You are like saying either please sort me the list in ascending or descending way. And the interesting part here is that you are just, what sorting algorithms are doing, they are trying to search for the one permutation, one of those permutations, which actually happens to be sorted. And unfortunately, you need to consider all of them in order for you to like say, okay, because I mean, you need to consider all of them in order for you to say that this list has actually been sorted appropriately. Because if you don't, what would happen is that you might miss on some of these permutations, right? So you might miss that one of them is actually like, if you skip any, you might miss one that's actually sorted, right? Or the correct answer. Um, so how this is actually being done, right? So this is a very interesting question. Um, right now, when we look at like comparison sorts in general, um, we actually let me actually draw the tree of permutations so you can see how things are actually going. But here I can just simply say that mm, essentially, just to make the material complete. Essentially, comparison sorts are slower than their counterparts, which is like okay. Now I should be back.
Yes, you are.
Okay, perfect. And I'll share my screen. I actually called our admin. Hopefully it will be resolved ASAP. Okay. All right. So, right now I'm actually using my phone hotspot, so I don't know if this how long this will be or how efficient this will be, but let's hope for the best. So we said essentially comparison sorts are slower than their counterparts, than their counter, because it searches. Okay, my writing is also going crazy here, so I'm just gonna continue the sentence right there. Okay. It searches through almost all permutations sometimes it eliminates half of them, depending on what algorithm you are doing. So bubble sort would be looking at all permutations, apparently. Quick sort shouldn't be, and so on. Through almost all elements, permutations. Let me minimize this. One by one, practically speaking, right? So this is why they're actually generally they are actually slower. Okay. So assuming that you are having, I'm actually going to write them in different colors so you can actually see like the differences. Assuming that you are having three numbers that you would like to sort through them, and I'm choosing actually three numbers because I don't want to write, if I write four numbers, I'm going to have to write 4 factorial, which is 24 permutations. The three would be quite huge. And I would like just to drive the point here across, so I'm just going to use three numbers. So imagine that you are having, let's say, so you have 8, 8, 3, for instance, and I'm going to pick up a different color, let's say blue, and I'm going to have here a 3, 7, 1, and then I'm going to have white, maybe, let it be Soviet, and then I'm going to have here 5, 9, and 6, okay? And imagine that you are having the three following numbers, and you would like actually to sort them, okay? What would happen is you would actually start considering what could be the possible combinations that you would like to, go through. And let's say that you are trying to sort the numbers from the biggest to the smallest, okay? So you have the following. Either your sorted list, the final list, either it will start with 8, 8, 3, or we'll start with 3, 7, 1, or we'll start with 5, 9, 6, so 596. If your tree starts, if the sorted list starts with 883, that means you have only two possibilities left. Either that you are actually getting one element following this. So you have either 371, which was colored blue, so 371, or it will be followed by 596, right? Because there are no other possibilities afterwards. So if your list starts, or the sorting, the biggest number, if this was the biggest number, then it's going to be just followed by either one of these two numbers, because you don't have any more of them. If you had more, you would have had the larger tree, obviously, right? You're going to have more choices. But right now we made it like three numbers because I don't want to write too much text, honestly. But this hopefully will drive the point across. So let me just write 6 nicely. And then right after this, so if you have a number, if you have 883 and then 596, then the only number which is left in the list, which is going to follow, is going to be 371, right? And this will follow it 596, right? So these are the possible combinations that could happen once you are actually having 883 as a 883 as a first number in the list. Now, if you look at 371 here, you have only two possibilities following that. So either you are going to have 883, so 883, or you're going to have 596, and then only two possibilities left. So 371 followed by 596 is going to be only number which is left, which is going to be 883. And then 883, so 371, 883, and this is going to be followed by 596, right? And let's move on with this one. So you're going to have, again, two possibilities. If your number or if your list or sorted list starts with 596, there's going to be only two possibilities. Either it's actually starting, or the element following that number is going to be 883, or 371, and then followed by that, either you're going to have so after 371, either you're going to have 883, or you're going to be followed by 371 here. Okay? So these are the possible combinations. This is actually the same thing as I've written it here, right? It is exactly the same stuff. I just simply written it in a different form, right? So that's that's one way to look at it, right? And obviously your permutation, which you are seeking for, if you are actually like getting from the smallest, or sorry, from the largest to the smallest, then you're going to actually have this permutation, right? Which is the sorted, this is actually the sorted list. So what you are trying to do here, you're just simply trying to, in a smart manner, eliminate each of the trees, each part of the tree, right? In order to get to this. So for example, if you look at this as a black box, right? If you don't look at the number, and then you ask, for example, okay, is 883 is less than 371, right? If it is no, then you are actually right now starting with this, for example, right? And then right now afterward, you start asking the question, is 596 is larger than 371? It is. So you actually, like, right now you are driving in here, and then you are asked, and then what is left is just simply the other number, and that's pretty much it. That's what the list is left. Okay, so you are just simply trying to break down with an if statement, if larger than or less than, and then you start actually like narrowing down the search through these permutations, and that's pretty much it. This is what like comparison algorithms, this is what they are actually practically doing, just through if statement, if larger than, less than, and with a little bit smart tricks, they start to narrow down the trees. And this is why you're always going to end up with n log n on average, right? So O of n log n. Okay. Does this make any sense?
Yes, it does.
Yes.
Okay, perfect. So let's talk about right now Radix Sort. But before actually I go to the Radix Sort, I would like actually to show you one kind of a sorting algorithm that you might find in the books. Let me actually check. It's actually, I think it's in one of them. They're the green, either the green or the white one from Mark Allen. Hang on, let me check. This one is called counting sort. And counting sort is very smart, very smart. But you're going to see the problem with it in a second. But it's actually super fast. It doesn't do any comparison whatsoever. And it is not stable algorithm. And we'll discuss this in a second. What does it mean a stable algorithm? What is not? Let's see. Actually, there you go. It's actually on page, so the algorithms 168, it's actually in the Introduction to Algorithms, second or third edition, 168 page. It mentions in there counting sort. But probably, yeah, there you go. But probably actually it just like mentions it as an ease in Introduction to Radix Sort. So there you go. It's actually like, so if you look at this in the book, it says like counting sort followed immediately by the Radix sort. Even though I actually would like to, I'm going to reverse the order of the book a little bit. So I'm going to discuss counting, then bucket sort, then Radix sort. or Radix sort with the counting part. But we'll discuss this in a second. Let me see the data structures analysis, algorithm analysis in C, if they have this also mentioned in here. Give me a second. So counting. Yeah, actually it is not actually mentioned here, which makes sense because I mean it's not that super popular, it's not super practical, but it's actually a good introduction anyway. So let me discuss this in a second. So this is the simplest algorithm. So counting sort. Let me make sure I write it down here. So counting, if I know how to write, counting sort. So counting sort is the, or one of the, let it be like one of the simplest algorithms that breaks, if hopefully the pen stops glitching, that breaks from the n log, oh man, n log n barrier. Okay, so that's what it is actually all about. It's like how do we break the n log n barrier? So I imagine that you have the following numbers, and I'll actually write it in yellow here just to stand out. So 5, 8, 4, 3, 2, 1, 1, 3, 5, 4, 6, and 0. So imagine that you have an array like this, okay? And you would like to sort this. What would you do is you will have to construct an array. So you have this is the input array, okay? So this is the input array. You're gonna have to construct something which is called a counter array, which is, it stands for counting, like counting array, you can call it that way as well. So you need to construct something which is called a counting array, which should be as large as the largest number in your array. So if I look here, the largest number in my array is 8, right? So right now I'm going to have a counter array or a counting array that actually has 8 slots in it. So it's a size of an 8. So I'm going to actually have, I'm going to actually write it like this. So 0, 1, 2, 3, 4. Oh, actually, let me write it in a different way here. So this is the 0th element, 1, 2, 3, 4, 5, 6, 7, right? We have 8. There we go. So at the end of the day, like we have like so. So this is the 0th, 1, 2, 3, 4, 5, 6, 7, 8 index, right? 8th index. So we just construct an empty array like this. And then what we do here is we start counting, right? We loop over the array. So let's say like this. So the first number you see is 5. So you say, okay, 5 has been seen once. So I'm just going to increment 5 here. 8 has been seen right now once. So I'm going to increment 8. Then 4 is going to actually be seen as 4. So I'm going to go to the index 4. I'm just going to increment it to 1, right? So I'm using this number as an index into my counter array, right? So if I see that, for example, when I said here's 5 when I first read the element from the beginning. Aha, okay, this is number 5. Go to the index 5 and put 1, right? So this is actually initialized all to zeros, by the way. So this is all 0, 0, 0, and this was 0 as well. So when I see 5, I just simply say +1. So it just simply added 1. And I saw an 8 right now next. So we are moving the next. So I++, let's say, right? And then you increment this to 1. Then I++, right? And you see here is a 4. You go to index 4 and increment this 1. And then I++, and then you see that there's 3. So 3 right now doesn't become 0. So you add 0 to 1, it's become 1. Then you move forward, you see a 2, you actually add 1. And then you see a 1, right? And then you see, aha, 1 at the index 1 is going to be, I'm just going to add 1. And then when I actually see another 1, I was just, okay, this is going to be incremented to 2, right? So there are 2 1s in there, right? And then when I go move forward, I see a 3, which is great. I'm going to increment this to 2. So I'm using this as an index into here, okay? And then I see, then we move forward, I see 5. 5 is here, 5 has already 1 element, it's going to be incremented up to 2, right? So just simply adding a plus. Hey, I saw 5 twice, right? Then we move forward, I see a 4. 4 is here, so 4 actually has been incremented to 2 right now. Then 6. 6 actually here, see, it's actually a 0, so we actually add to it 1, so it's going to be 1, right? And then we have 0, so we go to the 0th element, and it has 0 in it, so we add 1. And right now, we rewrite our input array, right? So when we rewrite our input array, and I'm just going to write it in red, I'm going to rewrite it as follows. So I'm just going to imagine that the input array is here, but this is right now the input array modified, right? So I'm writing it in red, so modified. Okay, so input array modified. So right now I'm just going to say, aha, okay, so I'm going to loop in 0. So the first, like, I'm going to go look at the counter array or the counting array. At index 0, there's 1. So that means I'm having 1 0 in here. So there's the output. So that 0 became here, right? And then I go in my for loop again, I just come here and say, aha, okay, here is at index 1, I have 2 of them. So I'm going to write in 1, 1. And then you move forward. At index 2, there is 1. That means I have only single 2 in that array. Then you move forward, and then you see, aha, there is at index 3, there are 2 3s. So I'm going to have 3, 3, right? And then at index 4, I'm having 2 4s. At index 5, I'm going to have 2 5s, right? So 1 more 5. At index 6, I have 1 6. At index 7, there is nothing, so I just simply ignore it. At index 8, I have 1 8, so I'm just simply going to have 8. And we are done. That's pretty much it. Okay? Right now, your list has been successfully sorted. No comparison whatsoever. Everything is just nice and dandy. The problem is with this sorting, however, even though it is fast, you need to allocate this array with the largest number in your list. If I actually just inserted here, let's say 10,000, right now you're going to have to allocate in the memory a 10,000 element array with the index, let's say 10,000 is right at the end. Right? So you're going to have a bunch of zeros until the end, like you're going to have a bunch of zeros like 0, 0, 0, 0, 0 until the end, which is 10,000, right? Which is going to have 1 in it, right? So you allocated a huge part of the memory just to sort 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 element array, right? So so this is actually not quite practical. I mean, it's super fast indeed, but it's not practical. And the complexity, by the way, of this thing is O of n. So you are actually sorting right now in linear time. You're not comparing anymore. You don't need to search for permutations. You're just simply blindingly pushing things forward. Okay. Does this make any sense?
Yes, it does.
All right.
Totally.
Any questions so far? None? Okay. So right now we understood like what kind of interesting sorting algorithms we can pull off right now without just comparing numbers. There's one variation of it which you see is a counting sort. Another way of solving the counting problem part, like how to, like instead of me reserving 10,000 element memory, another one would be like, okay, I can, let's say, use a different kind of sort, which is going to be Radix Sort, but with buckets, right? Right now they call it, we call it usually like, so let me actually draw a line here. I know how to draw a line without glitching. It's somehow glitching all the time, fortunately. So we're going to discuss right now bucket sort. Counting sort is like usually I use it as an introduction, and even in the books, actually it is there. I used as an introduction to bucket sort and Radix sort because it actually more or less it relies on this idea. In order to see the beauty of it, I'm gonna actually write a little bit larger numbers so you can see so you can see how this thing works actually. So I'm gonna write in a bunch of numbers here. So let's say that we are trying to sort an array which has the following elements. So 461, 771, 683, 883, 034, 405, 895, 966. Okay, so imagine that you have a list like this. Okay, now what we usually do is we're going to rely on the fact that when we are trying to sort numbers, we're going to rely on the fact that we are using the decimal base 10 numbers, which we are usually using in real life, like in math. No, I mean, we use different bases in real life as well, but let's say we are using the normal mathematical everyday, which we use it at work or like when you are buying stuff, you are not using base 2s, you are using base 10 decimals, right? So we're going to rely on that fact that we are trying to do that. And we are actually going to be sorting unsigned integers because signed integers are a little bit interesting to, it's a little bit of a special case, which we are not going to discuss here because you need to handle it in a different way. So unsigned integer means that you don't have negative or negative numbers. You always have positive numbers. All right. So what we're going to do is we are going to, when we see that these numbers, like the first step in the bucket sort, you actually gonna create an array of buckets, which practically speaking, an array of arrays. So I'm gonna actually like draw them in that way. So I'm gonna have like, this is the 0, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, 7, 8, and 9, right? And I don't need any larger number than this. This is the maximum numbers which I need. So I'm going to allocate in the memory a list which holds lists, right? So like, yeah, it's actually a list. This one, like, this is a list. This whole thing is a list. And each one of these elements is actually a list. Okay, so array of arrays, practically speaking. Okay. And what we're gonna do is how we're gonna have like this is what we like. These are the buckets. This is the first iteration. So these are my buckets. And we need to create, like, maybe we need to create an output array, maybe not. We don't. I mean, you don't need to create it. Actually, in this case, you don't need to create an output array or anything. And what you're gonna do is you're gonna start considering the least significant bit or the least significant number, or we look at the ones. So this is the ones, these are the tens, and these are the hundreds, right? And what we do is we actually start saying, okay, I need this number only. I need to check it out, right? So so let's actually get started with this. So I actually will try to write it down in an interesting way here. So I'm gonna loop here and say, okay, first element, get me the first element. So the first element is 461. If you would like to get this number, in programming, you usually say if this was equal to x, okay, then if you would like to get this number, you're gonna need to say x divided by 10 modulo. Well, actually, I mean, yeah, okay, if you want like to get the first number, this one, so it's gonna be x divided by 1 modulo 10, which is simply x modulo 10. And this will give you actually 1. So x divided by 100 modulo 10, or hang on, let me like 10. Let me actually do this in a neater way. You're gonna get 6, right? And then you're gonna have, like, if x divided by 100 modulo 10, you're gonna get number 4. Okay? I mean, your output will be literally this number. All right. So this is how to get the numbers in, like, each one of those guys in programming. Okay. So just to be clear in that part. So I'll actually like mark it. So right now I get this 461, and I look at the ones in the first iteration. Okay. So the first iteration, I'll look at the ones, and ones here. Here is actually number 1, right? So I will go to index 1. And I'll add it into the list. So right here, I'm just going to write in 4, 6, and I'll just simply write 1 here, just to denote that I'm looking at the ones element. Then coming up next, I'm going to look at this element, right? And I will extract the last digit in this 3-digit element, right? And it says here it's 1, so I'm going to go to index 1. I'm just going to simply write in 7, 7, 1. Right? Then we move forward, 683, we're gonna grab this number, extract this guy. So this is 3. We're gonna go to the index number 3, so 6, 8, 3, right? And 3 should be written in a different color like this, so we can keep track of stuff. And then we look at the next element, which is 883, which is gonna be 8, 8, and then 3, right? And then we have a number which is 34, right? But because we are evaluating 3 numbers, I just simply add a 0 in front, so it will be easier for me to evaluate, even though, I mean, it is meaningless in there, but it's easier to evaluate when you have 3 numbers, right? So if you have 1,000 as a number, you're gonna have a look at like 1,000, and then you're gonna have like number 3, so you're gonna have 0003, for example, right? If you have a number, like, let's say at the end here, you're just gonna add zeros in front of all of these guys, okay? Just to be clear here. Now let me carry on with this example. So 034, we extract number 4. So right now we go to the index 4, and we're gonna write in 034. Just write 034. We move on. 405, index we extracted, so 5. We go to 5, 405. We move on to the next element. It says 985. We extract the ones element, which is 5. we're going to write in, let me write 5 here, and then I'm just going to write in 9, 8. Okay, and then 966. And 966, it means that we have like, we're going to extract the last number, which is going to be number 6. So I'm just going to get in here and just simply write 9, 6, and then another 6, right? And then we are done, right? We just finished first pass of the array, right? So we looked at like each one of the last elements here, or the last digits, which basically the ones part of the number. Okay, now what we do, the next step is copy whatever we have here back into the array, right? So an interesting effect will happen actually, which you're going to see in a second, which is going to be kind of weird, but it just happened to be when I chosen these numbers at random, it happened to be like quote unquote sorted. So if I actually like write this down, I will go in a for loop, say, okay, at the 0th column, there's nothing in there, right? Then we move on to next one. And at the ones column, we have 2 elements, so I'm just going to copy those guys. So 461, then we pick up 771, right? And we are done with that. 2's column is empty, so we ignore. The 3 column, the column with the index 3, has these numbers. So 683 and 883, right? And in the 4 column, we have 034.
I'm sorry,
Yes?
but the number is 8. One of the numbers is 895. You have it written down in the 6th column.
Oh, sorry about that. Thank you for notifying me. Okay. 8, 9, 5. Thank you for notifying me. Probably, I missed that. All right, so 034. Imagine that people actually watching this video like later, or whoever didn't attend, and then they are just screaming at the screen like, "Hey, it's a mistake," right? But hey, it's corrected at the end. Thanks again. All right, so 5. So let's see. So 034. Then at the 5th column, so 405. And then 895. And then 966, right? And we ended up actually pretty much with the same array, isn't it? It's kind of crazy. But if you look at this, actually the last elements are actually sorted. So 1, 1, 3, 3, 4, 5, 5, 6, right? So it's kind of sorted. So that's why we got actually like an output of the same array. Actually, if they weren't sorted, actually like if it didn't happen to be sorted in that way, you would have had a completely different arrangement, which is kind of weird. But let's go on with the same methodology, okay? All right, so we ended up with an input array. In this case, luckily, or to our bad luck, that with the same sort, right? So this is right now our input array again. Okay. And right now we're gonna actually create. Right now we go ahead and we empty our buckets, reset everything. And then we're going to look at the tens side of the elements, right? So I'm just going to go ahead and write this down. So I'm going to have the zeros bucket, ones bucket, twos bucket. And I will just carry on writing this down. Oh boy, come on. Okay, I will not fight the glitch anymore. So just simply like, if it glitches, it glitches. I cannot do anything about it, right? So 9. Okay, so yeah, right now we look at the tens column, right? So we look at the tens digit right here. So these guys, right? And you extract them with this modulo bit. So right now you're actually getting the tens part of the digit, okay? So let's see here. So let's see here. So 461, 6 we are extracting here. 6 we're gonna index it right here, right? So we're gonna write in there 4, 6, 1. So this is 6, right? And then we move on, 771, so 771, so this is going to be 7, right? We extracted this one, so 771, and here's the 7, right? Moving up next, 683, which is going to be at index 8, so 6, 8, then 3, we have 8, and then 883, and then another 8, right? So this is 8, so right here 8, and then 8, 3, right? 0, 3, 4, which is going to be 3 at the index 3, so which is going to be 0, 3, 4. And I'm just going to write here 3. And then we consider 4, 0, 5, 0. So I'm just going to write here 4, 5, and then we have the 0, right? And then we have 8, 9, 5, which is going to be here. So 8, actually, let me write it then 9. And this is going to be 8, 9, 5. Hopefully, it stops glitching anytime. And then 966, which is going to be 9. Then we're going to have 6. And then 6. Sorry. It should be here. So 6, 6, 9, and 6, right? So at index 6. So right now, all the elements are being arranged in their own buckets. Are all arranged in their own buckets, like in that manner, right? So we are following the indices based on the tens in this second iteration, right? So this is iteration 1. This is iteration 2. And upcoming next, iteration 3. So we're going to have here another input array. Right now, we copy the stuff which we have in here into the input array, right? So we copy all the stuff from there into our input. So we loop. So 405 is going to be written here. Nothing in the ones, nothing in the twos. 0, 3, 4. Nothing in the 4, nothing in the 5. 4, 6, 1. 9, 6, 6. And then 7, 7, 1. And then 6, 8, 3. 6, 8, 3. And then 8, 8, 3. And then 9, 8, 9, 5, right? So this is our input. We are still not sorted yet. We haven't sorted the stuff yet, right? So coming up next right now, we right now need to look at the hundreds column. So I'll write this down again. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so right now we're gonna make our 10 buckets again. Okay, and right now we're gonna look at these numbers, right? So let me just mark them here. So this. Right now we're looking at these guys. Okay, and right now the first number will be 4. So we're gonna write in 4, and then 0, 5. Then the next number is going to be 0, 3, 4, which is going to be 0. And then 3, 4. And then we have 4, 6, 1, which is going to be at index 4. So 4, now 4, 6, 1. And then we have 9, 6, 6. So 9, 766, right? And then we move on, 771, which is going to be at index 7. So 7, and then 71. And then we have 683, which is going to be at 6. So 683, right? And then 883, which is going to be here. So 883, and then finally 895. And right now we do again the same, we repeat the same process, copy whatever you have in your buckets back into your input array. So when you do that, you will end up with the following. We loop over the elements, right? We loop over the counting or our buckets, basically speaking. So we end up with 0, 34. Nothing in the ones, nothing in the twos, nothing in the threes, and then 405, 461, 5, nothing in the fives, 683, 777, and then we move on here, 883, 895, 966, and we are sorted. All right, and our elements of the array has been sorted. How many iterations do we had? 3. Actually, you get number of iterations equal to the number of digits in your decimals. So if you had a 4-digit decimal, if you had a 4-digit integer, right, you will end up with 4 iterations. If you had 10 digits, you would have had 10 iterations, right? If you have million, you're gonna end up with 1, 0, like 7 iterations. So you're gonna do the sorting in 7 iterations if you have 1 million elements. Okay. Now the problem with this approach is that it is actually, like, even though that on paper it is super fast when you think about this, but it's still slow because memory allocation is actually slow. When you reserve a part of the memory and you keep freeing that memory and reallocating it again and freeing it up again and hunting for the memory pointers, right? So if you actually implement this as an integer list or as a linked list, actually it should be like a linked list because this is automatically expanding arrays, right? If you are doing the C++ way. If you are not going to use linked list, then you're going to have to do like automatically expanding arrays where you actually dispose the array and allocate a new one and copy the old elements to the new elements with a double of the size, right? So memory allocation will be quite expensive, actually, to do this, right? So this is bucket sort. So if you don't have a problem with memory, probably you can go with this one, probably, right? It's still not that super efficient though, right? So is there anything better we can do, right? And yes, there is a possibility to do that. So basically bucket sort is actually like Radix Sort with buckets, actually. Okay, but there is actually a Radix Sort with counting, which is one of the super efficient way of doing this. Actually, I'm thinking about like the problem here is I'm actually on my phone right now. I'm actually streaming from my phone. I would prefer to finish the whole thing right away, and then we're gonna give you a big break until programming 3, if it's okay with you guys.
It's okay. I just have a question. So what is the time complexity of bucket sort?
Oh, it is what was it? It is actually a linear one. It's actually a linear complexity. It is almost O of n, but it's the amount of iterations. So like what, O of n plus m? Hang on, let me actually double check my notes here. So complexity of bucket sort. It's actually like, yeah, it's O of n plus k, which is the amount of iterations that you need. So k is the iterations basically. Right. So yeah. Moving on then, let's talk about the Radix sort right now. Radix sort, the vanilla version of it. There are many variations, by the way, of many sorts in the world. Right now, this is the fastest sorting algorithm we know of. There are actually maybe faster. There are some has been introduced quite recently. I really cannot remember right now. Like quad sort, I think there's. I think quad sort was introduced year 2020. I cannot remember honestly right now. Don't take my word for it. You need to search for it. There are actually, like a fun fact, there are actually like some of these ridiculous sorting algorithm, like Stalin sort, and like for example, remove elements which are not in order and leave elements which are in order, and then do the iterations of n squared. You have you have something which is called the hope sort, which means that which usually, but this one is a computer scientist jokes, like return the same array. When you get the array, return the same array on the hope it is already has been giving you sorted, right? So you have something which is called the hope sort. But in any case, these are just fun facts or fun jokes, if you will. So Radix sort. And let me write it like Radix sort, or Radix, or sometimes they call it Radix sort with counting right now. This one is really, really fast. And quite efficient, actually. You only need to allocate two things. You need to allocate, like, it's the same as, it is similar to the bucket sort in terms of how many elements you need to allocate in terms of the counting. So you allocate counting from, is hope sort is going to be on the exam? No. Come on, man. This why would this be? So in any way, in Radix sort, imagine that we're gonna actually get the same, like I'm gonna give the same example, so I'm gonna use the same numbers. So let me just draw a line here. So I'm gonna have, imagine that you are assuming to get to the following. So 4, 6, 1, and then 7, 7, 1, 6, 8, 3, 8, 8, 3, 0, 3, 4, 4, 0, 5, 8, 9, 5, 9, 6, 6. Okay? So imagine that you have the following number, right? Like array. What you're gonna do is you're gonna actually have to what you're gonna have to do is you're gonna need to create two arrays actually. So let's write it here. So we need to create two arrays. One is the counting array. Two is the output array. Okay. Now this one is going to be fun. So, and by the way, the radix sort with counting will give me exactly the same output as radix sort with buckets, right? So it's going to be exactly the same output in every iteration, obviously. I'm going to actually like write indices really small here. 4, 5, 5, 6, 7. Okay, and I'm going to create a count array. So we have output array. Which is going to be, I'm going to actually like write indices really small here. So 1, 2, 3, 4, 5, 6, 7. The output array obviously is as long as your as how many elements you have in your array which you would like to sort. And then we have the count array, which is base 10, because we're actually sorting base 10 numbers. So we have from 0 to 9. So you're going to have a counting array. Which is going to be from 0 to 9. So I'm just going to simply like create another one. So 0, 1, 2, 3, 4, 4, 5, 6, 7, 8, come on, 9. Okay, so let's say that you have a counting array that looks like this. So what we're gonna need to do here is we're gonna look at, again, the same way as we did before. We're gonna extract like the last digit, like the ones digit, let's say. So we're gonna extract the last digit here. We're gonna look at it. And then we're gonna actually like increment the counter of these digits. Okay, so I'm gonna actually start from here. So I'm gonna start from here. So let's say, so this is 461. So first of all, the counting array we look at here, this is actually going to be, by the way, all of this is set to 0. So 0, 0, 0, 0, 0. All of these are zeros, okay? Just simple zeros. And right now here, we encounter the first element. It's going to be 461. So we increment this to 1. Right? We add 0 to 1. Right? So we've seen it once. We added 1. Then we move on. We say, okay, 771. Right now we have 1 at this index. So this one indexes me through here. Okay? And I see there's 1 in here. So I'm just going to bump it up. So it's going to be 2. And then we move on. 683. So it's going to be 3 here. So we're going to increment this to 1. We move on forward. This is going to be 3 again. So we bump it up to 2, right? And then we have 0, 3, 4. 4 is going to be at index 4, which is going to increment it to 1 right now, right? 5, so 0, 4, 0, 5, we extract that number. We see that 5 is here. 5 increments to 1. And then we have another 5, which is going to be increments to 2. And then we have 1, 6, which is going to be incrementing to 1, right? And the rest is zeros, okay? The next step, so next step is to do something which is called a prefix sum. And that what practically means is that you take the previous element in the array, add it, so you take the current element and the previous element and you add it together and you record it in the current element. So this guy doesn't have any previous, so this will stay 0, okay? Moving up next, this is 2, and this is 0, right? A prefix sum will say 0 plus 2 is equal to 2, right? And then we write 2 here. So right now 2 will not change. It will be staying there. So let's move forward. 2 plus 0 is 2, right? So 2 plus 0 is 2. We take the 0, we replace it with 2, okay? Actually, I'm going to replace this. I'm going to write this updated prefix sum like this. So I'm just going to write in 2, and this became 2, right? I'm going to just override it, and this became 0. And right now, so 0 plus 2, 2 plus 0 became 2. So let me actually write this. Hang on, sorry. So this was 0. Right now it became 2, right? Now 2 plus 2 is actually equals to 4. So we grab this, and this will be hang on, so 0 plus 2 is going to equal to 2. We register it here. 2 plus 0 is 2. We're going to register it here. 2 plus 2 is going to be 4, and we register it here. So this is going to be 4, right? And then 4 plus 1 is going to be 5, and then we register it here. Then 5 plus 2 is going to equal to 7, and we register it here. 7 plus 1 is going to be 8. We register it here. 8 plus 0 is going to be 8. 8 plus 0 is going to be 8. 8 plus 0 is going to be 8. Okay.
Just one question.
Yes.
Isn't it gonna be 2 plus 3 is 5?
Where is 2 plus 3 here?
For the third element.
Which element you said?
For the third one. Index of the third
3?
element.
Yeah.
Plus 2, right?
So it was 2 here, and there was 2 here, right? So 2 plus 2 is 4. Where is the 3? Hang on. Here's the... Hang on. Let me write this. Wait, there was 2 here, right? Before.
Yeah, 2.
Okay.
Yes.
So 2 plus 2 is 4. And we put here 4, right? So this is not 2 anymore. Am I missing something?
No, I think you are right.
Okay. So at the end of the
Okay,
day, we end
sure.
up with... Excuse me?
No, it was my mistake. I'm sorry.
Okay, all good. All good. It's always nice to double check. So 0, so we ended up with 0, 2, 2, 4, 5, 7, then 4 8s, right? So this is not zeros anymore, right? After the prefix sum, or 1, 0, 0, 0, right? It became these numbers, right? So what do we do next? Right now, after we did the prefix sum, sorry. Once we done this, we start from the right side here, and we fill in our output array. Okay? So starting from the right, we say, okay, so this is 966. We grab actually 6, right? We are looking at the ones. So we grab 6, it is here. We look at this part. These numbers, which you see here, became our indices into the array. However, these indices are base 1, and our array is base 0, quote unquote. So what we do here is, whenever we say, okay, this is 966, we grab the 6, we look into it here, right? It gives me index 8 minus 1, so we need to subtract 1, and then I'm going to write it here. So 966 becomes here. Okay, moving up next, 895, this is 5. Oh, by the way, and you subtract that. So right now this becomes minus minus, so you take this out, this becomes 7. So that's just to be clear here. Now, 895, so we take the 5, index it somewhere, there you go, it's here. You look at it's right now it is 7. Minus 1 is going to be 6. So this is going to be 6. And right here we're going to insert 8, 9, 5, right? And you carry on with that logic. 5, right? You index it again here. You see we have a 6. We subtract 1. This is not 6 anymore, it becomes 5. And we take this number, we put 405 in place. Right? Are we good?
Yes.
Okay. So we keep doing this.
Do you mind just repeating that last part? Minor now.
Last part where? Which last part? Like with the one with the 405?
Yeah, so when we take a number, for example, 966, and then we go to index 6, why
We go
do
to
we...
index 6. We
Okay.
we look at, it's actually 8 here, right? These are
Okay.
indices into this array. But this is base 1. So I need to subtract 1, right?
Okay.
If this was based 1, this would have been 8, and I would have injected it directly, right? I didn't have to subtract 1 anymore. But this is 0 based, not 1 based. So that's why I have to subtract 1 in order for it to go in position here. This is clearer now, or?
Yes, thank you.
Okay. All right. So again, moving along. So 034. We take this. We go here. So 034 is pointing at this one because we take number 4 this one. It is at index 5 because again our array is 0 base. We need to subtract from 5 1. So we're gonna just simply, this is not gonna be 5 anymore, it's gonna be 4. And right now this will be 0 3 4. Now obviously if I go carry on with this logic, we're gonna end up with 883 683 771 and 461, right? Exactly the same way for the first iteration when we ended up with the buckets actually, because, and this is for the reason because our array actually was sorted when it comes to the ones bit, right? It was already sorted. But once we finish with that output array, right? So the output array is done. Copy the output into the input array, clear the output array, and reset the counting array. Okay? So after you're doing the prefix sum, grab the arrays and grab the number. Gotta grab. Okay, so next step, do a prefix sum. Next step. Start from the end of the input array. AKA from the right. And check the ones digit, right? So that's the main point. Index through the counting array, subtract 1 from whatever number is in the counting array, and put it in the correct index in the input array. Oh, sorry, in the output array. And now, so this is the next step. Next step, copy output into input array. Okay, clear output array. Reset the counting array. When I say reset, means that you're going to loop over every element here and just set it to 0. Okay. Now let's do one more iteration just to make it clear, because right now it's going to be similar output to the bucket sort, but just to make the things clearer a bit. And then then you guys can take on with the third step, which is the final step, where you're going to actually get the elements sorted, right? Or actually, I can actually jump ahead. How about this? Would you like me just to jump one more step? So instead of doing 2 iterations, I'm going to say that the second iteration is done. I'm going to make the final iteration, and then we go with it if you want to. Or actually, I can give you like the second iteration, then you complete the third iteration. You pick, because right now we are running out of time. So, what do you guys think?
Yeah,
Maybe you
whatever
can
is
do the
easier
second.
to you.
Excuse me?
Maybe you can do the second one and then we can finish the last one.
Okay, so let me do the second iteration then. So the second iteration would be, we have already the output array. So let me actually like write down this thing again. So I'm gonna write it down here. So second iteration. Can I actually, if I select this, do I have the ability to copy? I have no idea. I'm with a pen right now. Or maybe. Aha, copy. And then I'm just gonna, come on. Can I paste somewhere, please? Okay. There's no paste, isn't it? Yeah, this is fun. Okay. Okay, I'm gonna write it down. Who cares? It's gonna be faster then. 461 771 683 883 034, and what was it, 405, and then 895, and then 966. Okay. All right, now the second iteration. Again, we have our counting array is going to be like so. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So this again, this is, for heaven's sake, stop glitching. So this is base 10, and we have the output array, which is actually like nothing is in there. This is already a reset, so everything here is actually 0. Output array is the same size as our input array, so this is where we're going to do our output. Next iteration, the same as we did before, we're going to actually examine right now the tens, and you guys then do the hundreds. Okay, so we examine the tens, and then we say, okay, 461, we have a 6 right here, we index here, so we increment this, we add 1 to the 0, which is going to be 1. We go to the 7s, and then we have, the 10s, so 777, 71, sorry. So 7 here is going to be indexing right here, so we're going to actually increment this to 1. 683, we go to the index 8, and then we increment this to 1. 883, we go to index 8 again, we see we have a 1, so we increment this to 2. 034, so we go to index 3, we increment the 0 to 1, so we add whatever value to whatever existing in the counter. 405, we have 0 in here, we increment this to 1, so we add 1 to the 0. 895, we have this 9 right here, so increment this to 1. 966, we have a 6 in here, so we go back in here, we have 1 in there, so we're going to increment this to 2. And right now, we are done with the counting. Next step, prefix sum. Now, the prefix sum, again, says that you need to sum the two elements and record it in the last element which you added. So right now we say the zeros column will be always the same. It will stay because this is the first one. There's nothing before it. Now, next 0 is going to be 1 plus 0 is going to equal to 1. So this becomes 1. Right, so let me write this in red if you want to. It will be obvious. Then next, 1 plus 0. So if I'm actually trying to find out what is the prefix sum of this guy. So 1 plus 0 is going to be 1. We record here 1. Now, coming up next, this prefix sum of this element is going to be the element plus the one previous to it, and record the result here. So 1 plus 1 is going to equal to 2. And then this element is going to be like 0 plus 2 is going to equal to 2. And then 0 plus 2 is going to equal to 2. Then 2 plus 2 is going to equal to 4. 4 plus 1 is going to equal to 5. 2 plus 5 is going to equal to 7. 7 plus 1 is going to equal to 8. Okay, so we have 1, 1, 1, 3 2s, 4, 5, 7, and 8. Okay, now we need to copy the result in the output array. So I'm just gonna this is 0, 1, 2, 3, 4, 5, 6, 7. So I'm gonna have an output array which has 0, 1, 2, 3, 4, 5, 6, 7. Okay, and right now we start again from the right, so we start from here. Okay, and then we say, okay, we check for the tens. So this is 6. We have it here. So 6 would actually point me to the index 4. Right now we have an array of indices, right? It points me to the 4th index minus 1 actually, because we are having a 0-based array. So right now this becomes 3. 3 is going to be right here. So I'm going to write there down 9, 6, 6. Okay. Coming up next, 8, 9, 5. 9 is actually pointing me here. We have an 8 minus 1 is going to be 7. This 7 will show me the way to here. So 8, 9, 5. Coming up next, 4, 0, 5. 0 is actually pointing me to the 0th element, which we have 1 minus 1 is going to be 0. So 0, 4, 0, 5 is going to be at the beginning. Okay. Coming up next, 0, 3, 4. 3 at the index 3. We have a 2 in here. Minus 1 is going to be 1. We're going to have 0, 3, 4. Then we have 8, 8, 3. So 8, 8, 3. So at this index 8, we have a 7. Minus 1 is going to equal to 6. So 6, we're going to have here 8, 8, 3, right? And then let's see, where are we right now? 883, 683. Right now it will drive me again to here, which the last element, the last number was 6. We're going to subtract from it. It's going to be 5. 5 is going to be right here. So 6, 8, 3. Then 7, 7, 1, 7. At this index, we have a 5. Minus 1 is going to equal to 4. And 4 is going to give me an index right here. Then 4, 6, 1, which is going to drive me here. We have a 3 in there. Minus 1 is going to be equal to 2. And then we're going to go to index 2 and we're going to have a 4, 6, 1. Okay? Copy the output into the input array, reset your counters, and do the final step. Once you do the final step, you're going to get actually a sorted array. Okay? The time complexity is actually similar. It's actually O of n plus k. However, you are actually consuming much, much less memory. You are actually, you're going to allocate 2 arrays. One of them is going to be the same size of your current array. So if you have 1 megabyte array, that means that your sorting requires that you have 2 megabytes free memory. So 1 megabyte is for your input, 1 megabyte for your output, and you have, for example, additional a 10 element list, which is, I don't know how many kilobytes is that. So you end up with that size, okay? And once you are done with the sorting, this is it. Now, just kindly note that quick sort, for example, in most cases is super fast, is super fast actually. But once you get into elements that are beyond 100,000, 1 million, 2 millions, right now Radix Sort becomes much faster than the quick sort. It gets faster by orders of magnitude actually, if you even test this with a timer on a computer. But Radix Sort obviously will start jumping up higher in the memory side. So there's nothing coming for free. You either win speed with more memory consumption, or less speed with less memory consumption, right? So you cannot have it all, practically speaking. So yeah, this is what Radix Sort and counting sort is all about, and the difference between it and the rest of the comparison sorts. Any questions so far?
No, it's clear.
All right, perfect. All right, then I'll give you a little bit longer break. So we're gonna meet at 1:15 again. So see you back then. By then.
Okay, thank you. Bye.
Bye.
Great, thank you. Bye-bye.
Bye.
Thanks.